In this next video, we are going to look at some applications of trigonometry, basically what we've been learning with sine, cosine, tangent, things like that, how to apply that kind of information to solve some other problems. And first, we're going to look at one very specific use of sine, cosine, and tangent, really just sine, and that is in an area measurement formula. Okay, this is a unique area formula for any triangle. And we could go over where this comes from and how it works, but basically all we have to do is take a look at this formula for any triangle where we are given two sides of a triangle and then the angle between those sides. So like side, angle, side. So you'll notice on all these examples, I'm given two sides and an angle between, two sides and an angle between, so on and so forth. And so what we notice here in this application is that the formula is 1/2 of one side times the other side times the sine ratio for the included angle. Okay, notice the angle C is always between, or the included angle, of the two given sides A and B in this case. Now, you'll notice that there's this H here. I don't need the H. It's not part of my formula. So we're just looking at this formula. Okay, and this is going to be lesson 5.6, or day 5.6. We're looking at applications. All right, so we're looking at applications, and this first one is using area, and really all it is plugging into this area formula. So in this case, if I've given this triangle, this is an 87-degree angle here. I don't know either of the other two angles. It might be a right triangle, it might not be. In this case, it probably wouldn't be because this is 87 degrees, but that really doesn't matter. This is our angle C. And then these two sides are our A and B. And so all I have to do is plug into this formula. They use capital K here for area. It really should be capital A, but it doesn't really matter. We're going to do half of that A value, 8. So 1/2 times 8 times the B value, 6, times the sine ratio, and it's always sine, of that 87-degree angle. And so by plugging all of this in, sorry, hopefully you saw that. By plugging all of that into the calculator, I can do it all in the calculator at once, I will get my final answer for area, and we're going to round to the nearest tenth. Okay, so we're just going to plug this in exactly as it's written. Now, you can plug in 1/2 a couple different ways. I like to just leave it as a 1/2, and so to do this as a fraction on this calculator, I just use parentheses, 1 divided by 2 parentheses, and then times 8, times 6, times the sine ratio of 87. And then close your final parentheses after the 87, hit enter, ignore that bell, and you get a final answer of about 23.9671, so on and so forth. That is your area in square centimeters. So we're going to round that to the nearest tenth. Because this 6 follows the 9, we're actually going to round this up to 24.0 square centimeters. Leaving that 0.0 shows that I've rounded to the 10th place. Okay, so let's try one more. All right, we've got a 140-degree angle. Notice this can't be a right triangle, but our formula still works. And then that means that's our C for our angle. And the two sides, A and B, are 6 and 5. And it doesn't matter which one is which. You could switch those two, as long as you use 140 degrees for C. So our area is 1/2 times the A value, in this case I said it was 6, times the B value, which I said is 5, times the sine ratio of a 140-degree angle. Plug all that into the calculator like this. Sorry, like this. 1 divided by 2 for my 1/2 times 6 times 5 times sine of 140, close those parentheses, and you get 9.6. This has a total area of approximately 9.6 square inches. Don't forget units of measure in our application problems. A lot of the time we will be using units of measure, so our answers will need units of measure. Okay, and that's how we can use the area model. We're going to skip over these next two. If you want to try them on your own to see if you know how to do this, that's fine. We'll take a look at those in class. Okay, the remainder of this video, we're going to look at some specific kinds of word problems that use two special kind of angle problems called angle of depression and angle of elevation. In this case, elevation would mean something rising up or looking up, and depression would be something sinking down or looking down. And a lot of this deals with an angle formed by a line of sight. And so we will either have a person or something that has a line of sight to a point above or point below their normal horizontal line of sight. And that creates these angles of elevation or depression. So let's look at this first. On our page for angle of elevation, when looking up to an object, the angle of elevation is formed by an observer's line of sight and a horizontal line. So it's like this. So we have an observer here, a person, and standing tall and looking out horizontally creates this imaginary horizontal line. And as soon as they look above that horizontal line to a point above their normal height, you're getting an angle of elevation. Whereas on the next page, if we had an observer looking straight out and they looked below to a point below that normal line of sight, you get what's called an angle of depression. And that ends up creating some right triangles using horizontal and vertical measurements where that line of sight ends up being a hypotenuse. And so what we can do is we can work through some of these problems by drawing that right triangle. So let's take a look at example 1 under the angle of elevation. First thing we're going to do is draw and label a diagram, and then we're going to solve for the missing piece of that picture in the real world example. So here's our first example. Casey sights the top of an 84-foot tall lighthouse at an angle of elevation of 58 degrees. If Casey is 6 feet tall, how far is he standing from the base of the lighthouse? Now there's actually two parts to this problem. It is exactly drawn like this. We're going to make it a little more simple. Okay, we're just going to put a point for Casey's line of sight, or where it begins, his eyes. Okay, and then we're going to draw a horizontal line out. And he looks straight out at the lighthouse. So this is our lighthouse here. This is not going to be drawn to scale, obviously. But Casey is 6 feet off the ground. Okay, so there's a 6-foot measurement there, which means this measurement here is also 6 feet. So 6 feet of the height of the lighthouse is already given to us. The right triangle comes when Casey looks up at an angle of 58 degrees. Now, that is given to us. They also tell us that the top of the lighthouse is 84 feet above the ground. So this entire height is 84. Well, that creates this right triangle, but this opposite leg of the right triangle is not 84. It's the difference of 84 and 6, meaning we're going to cut off the 6 feet of the bottom of the lighthouse and realize that 84 minus 6 is 78 feet. So this leg of your triangle is only 78 feet. Okay? And so what they ask you for is how far is he standing from the base of the lighthouse. So we're looking for this, because that length from his eyes to the lighthouse is the same as from his feet to the base of the lighthouse. Okay? So this is a very complex drawing, but the problem gives us everything we need. And notice that his line of sight, we're not actually measuring that, we're measuring this horizontal distance. So that's our x value. Well, what that creates is a right triangle where I have an angle measure. This is your angle measure, your reference angle. I have this leg that I'm looking for, which would be the adjacent leg. And I have this leg that I'm given, which would be the opposite leg. Since I'm using the opposite leg to help find the adjacent leg, you need to remember the TOA part of SOHCAHTOA, and we're going to use our tangent ratio. So the tangent of 58 is equal to the opposite leg of 78 over the adjacent leg, x. And you'll remember from our last lesson then that we put this over 1 to create it as a proportion so we can cross multiply, putting x in front of tangent 58 for multiplying those, and then 1 times 78 is 78. Now all we have to do is divide by the tangent ratio of 58 on both sides, and that's where our calculator comes in. When we divide like this, we get that x is 48.73. Now we are to round to the nearest tenth, so that's actually 48.7 feet that Casey is standing away from the base of the lighthouse. Don't forget the units of measure. Okay, we're going to go ahead and move on and do a problem that uses an angle of depression. Okay. Whereas we're going to have a horizontal line of sight originally, and then we're going to drop our line of sight below that, creating an angle of depression. Okay. Now I do want to point this out before we go any further. When I use this picture of a lifeguard watching a swimmer, the lifeguard has an angle of depression to the swimmer, but when I look at this from the swimmer's perspective, his angle of elevation to the lifeguard would actually be congruent to the lifeguard's angle of depression. And that's what that states there. And this is because the horizontal line from the lifeguard is parallel to the horizontal line back from the swimmer. Since those lines are parallel, these are alternate interior angles. And so sometimes this angle of depression ends up translating to this congruent angle down here, and I'll show you why we do that in this example. We're going to look at number 6. Okay, we're going to skip over number 5, look at number 6 here. We've got a pilot in a helicopter that spots a landing pad below. Now, so what I've got is a point up here for the pilot, or sorry, for the helicopter. I'll use an H for helicopter, and his landing pad, L, down below. The angle of depression, so from the helicopter, so I've got this imaginary horizontal line up in the sky. His angle of depression down to the landing pad, that was a pretty crooked line. That's all right. That angle of depression is 73 degrees. And the horizontal distance to the landing pad is 1,200 feet. So if I drop straight down and measure the distance along the ground, that's 1,200 feet. And they ask, what is the altitude of the helicopter? That's how far in the air it is. That's what altitude means. But I want you to be careful of something. This 73-degree angle is not this angle inside the triangle. So H is not actually a reference angle. I want you to remember that the angle of depression is congruent to the angle of elevation at the end of that line of sight. So if this is 73 degrees, so is this. So I'm actually going to use this as my reference angle in my triangle. That makes X the opposite leg and 1,200 the adjacent leg. And if you get these backwards, you're going to get wrong answers. So that's why I always translate my angle of depression down here to my angle of elevation. So we are going to go ahead and set up our tangent ratio again. You'll find that most of the time for angles of elevation and depression, we'll use tangent. So the tangent of 73, because it's opposite over adjacent, equals X over 1,200. Now, you could still set this up as a proportion, but all we really end up doing is multiplying by 1,200 on both sides. And when I multiply, I get an X value of 3,925.0, so you wouldn't have to put the 0.0, but we're going to, feet. And that's how far into the air the helicopter is. That's its altitude. So we're going to do some more examples with angles of elevation and depression, but the trickiest part about this is actually setting up your pictures correctly. So we're going to spend some time in class going over how to make sure we set those up correctly. You don't have to be an artist to do these drawings. You just have to be able to draw right triangles and interpret the right pieces of information from the given problem.